Welcome to this lecture on steady state solution to LQR. We will motivate steady state LQR law. We will derive an expression for this law. Recall that we derived the control law as a time varying one. We are interested in a steady state solution. The reasons are: the constant solution is easy to implement. Even in time varying solution, the control law could be constant most of the time. When J has infinite number of terms, known as the infinite time problem, steady state solution is the optimal solution. That solution is presented in this lecture. We will not derive it, we will only state the solution. Recall the discrete time Riccati equation. The steady state solution is given here. Because it is steady state, we have Sk equals Sk plus 1 equals S infinity, that is for large enough values it is constant. As a matter of fact, it is constant throughout. So we will just replace all the time varying quantities here with S infinity, namely a constant value, and arrive at this expression. We can solve this by iteration, but it is not an easy problem. We will construct the following control Hamiltonian matrix HC given here. This will help simplify the solution, as we will see shortly. The steady state solution to the Riccati equation is given by the following: lambda I into xi inverse, where xi lambda I transpose is the eigenvector of HC. Which eigenvector? Because HC could have many eigenvectors. What you have to do is group all stable eigenvalues, collect the corresponding eigenvectors, call that xi lambda I transpose, and find this expression, and that is S infinity. The steady state control law is given by this expression, minus k infinity into x of k, where k infinity is given as a function of S infinity as given here. This is something we derived already. Only thing is, wherever we had S as a function of k before, we have to replace it with infinity, because S infinity is constant. The performance index for the steady state control problem is given here. In the place of time varying S, we have replaced it with the constant value S infinity. As before, this control law k infinity can also be calculated once and for all at the very beginning. To conclude, we presented a steady state solution to LQR. It gives a constant control law. It can be calculated once and for all at the beginning itself. This is a basis for several state space control laws. It is important to notice that we assumed the availability of the state vector x. When states are not available, we estimate them. That estimator is known as the Kalman filter. LQR used with Kalman filter is known as the linear quadratic Gaussian or LQG controller. State space methods provide an attractive alternative to the polynomial approach. Of course, in this course we followed the polynomial approach most of the time, but it turns out that the state space approach is more popular. Many more results are available for state space methods. Nevertheless, these two methods are equivalent: polynomial approach and state space approach. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.